Go through this. We're going to talk about where's my camera? Right there. We're going to talk about three different formulas that we need to understand so that we can solve unknown information on tapers. But there's a practical piece to this, obviously. A lot of times in manufacturing, we have to cut a taper, whether we have to create a tool path for a end mill on in a milling project, or we have to create a taper on a lathe. So there's some things that we need to know about tapers. Where's my pen? There we go. So what we're going to do is we're going to talk about three things. Number one, we're going to talk about taper per foot. Okay, taper per foot. And you'll see that referenced as TPF throughout the lesson and any assignments you get. Okay, so basically what this is you can imagine seeing a part set up on a lathe, and when you get that part, it comes in raw stock, it'll be one diameter, right? So you're going to put that diameter in 3-jaw chuck, you're going to clamp it down, and maybe it's long, so you got to face it off and you got to put a centered hole in it, right, and then support it with a tailstock. But whatever the case, you've got a piece of raw stock at a specific diameter. So you'll either have to create a specific taper according to a major diameter that's given to you and a minor diameter that's required. So you'll have to create a taper so that the minor diameter, the requirement is met on the print. Or perhaps your print will call out, I think what print you guys are using at the college is you're using a print that calls out on your part a 2-inch taper per foot, if I remember correctly. So that 2-inch taper per foot, what that essentially means is that part, if that piece of material required a taper that was 12 inches long, by the time you started your tapers, and by the time you finished your taper rather, and you measured the taper at the large end and you measured the taper at the small end, you would notice a 2-inch difference in diameter. So if the part was a 4-inch diameter piece of material and you set up a taper cut and you did the math for a 2-inch taper per foot over that 1 foot of length, your part would get smaller by 2 inches. So you would essentially cut 1 inch of material off per side, right? So that's what taper per foot is how much the part reduces in size over 12 inches. So we need to know how to solve that, and we need to know how to apply it. The other formula we have to discuss is your tailstock offset. So taper per foot is a requirement for the part. Okay, so how much the part has to change over 12 inches. Tailstock offset is about setting up the machine. It's about how to adjust the tailstock in or out. And as you adjust the tailstock in or out, obviously the part has to be supported in the tailstock, right? So if the part is supported in the tailstock and you push the tailstock away, you're going to push the part away at the tailstock end. So tailstock offset, there's a formula that we can use so we know exactly how far away to push the tailstock or bring it towards you, the operator, to manipulate that piece of raw stock so that when you just run a linear cut, it creates a taper. And if you have not had a chance to cut a part using the tailstock offset and you have extra time, and Rob has the time, I would recommend that you get some help in setting up the tailstock so that you can cut a taper by offsetting it. So we're going to learn the formula for that. And then finally, we're going to solve the what is it? Setting the compound rest. Compound rest. Once again, this is a second way to set up the machine so that we can create a taper. Now, the difference is with the tailstock, so I don't know if how familiar you are. Let's just imagine this giant cutter, okay? Let's imagine this is the piece of material that you need to turn down. So if I have my center, so if you don't know this, you don't have to have a 3-jaw chuck clamping. You don't have to have a 4-jaw chuck. You can actually put a center in the headstock, a dead center, okay? And then a drive dog, which will spin your workpiece. And in this side, you would have your tailstock, right? So your part would essentially be sitting between centers on the lathe. So if that's the case, obviously you don't want to be grabbing this side and then push the tailstock away. You'll just mess up this end of the part, right? So if you're clamping this and then you force the end away, you're gonna damage this end. So you want to have the part sitting between centers, and that way it can pivot, right? It will pivot on this end. So with the tailstock offset, what's happening is, let's imagine we're looking down on the lathe now, okay? We're not. So with the tailstock offset, if I push the tailstock away, it's going to push the end away with the tailstock because the tailstock is sitting in here, right? So we're looking from a bird's eye view, right? So if you're the operator standing here and you push the tailstock away, the part's going to move with it. Or if you pull the tailstock in, the part's going to move with it. But you're considering that it's actually manipulating the entire length of this part. It's the whole part, right? It's pivoting on this headstock end up here. So the whole part pivots on the headstock end. Whereas with the compound rest, you're not adjusting the part. You're just adjusting the compound rest to create a taper. You set up the compound rest to take the taper you want. So how do I know if I use the compound rest or I use the tailstock offset? Well, with the tailstock offset, you can manipulate the entire length of the part. So you can actually create a much longer and a much shallower. You have much more control over that taper. If you don't need your mics on, guys, if you could just turn them off for me, please. If you have a question, I'm open to answer it, though, if that's what the mic's on for. I can't see who it is. So anyhow, with the compound rest, what we'll do is we will leave the part set exactly like it should be between centers, or you can have it clamped in a 3-jaw chuck and tailstock support because we're not going to be pushing the part around. And then you just adjust the compound rest and then you dial the compound rest, and that compound rest will follow that angle. The only downside to using the compound rest is it's limited to creating very short and very steep tapers. So you got to decide what you're going to use before you use it. Okay, so what we want to cover here is what information do we need to figure out taper per foot. So we need a couple of things here. So first thing we need to have or need to solve is this is the LOT. Okay, LOT, length of taper. Okay, this is not the hypotenuse, right? This is not the length of this side. This is the distance from the front to the back, right? So it is not this length. It's this length, which you and I both know are two different things, right? This is the hypotenuse and this is the base length. They are not the same. So just good for you to know that the length of taper is a true length, okay? It is not the hypotenuse. The other thing that we need to know or solve wow, my art skills are amazing today, is this here. Okay, the big D is the large diameter. So we need to know the large diameter, and usually that's going to be your material stock or a diameter that you've previously cut, okay? And then we need to know, obviously, the small diameter, right? Small d is the small diameter. Come on, you. Okay, so 3 pieces of information: length of taper, large diameter, small diameter. So to solve taper per foot, the formula looks like this. And if you're wondering if this will be on a test, yes, this will be on a test. To solve taper per foot, we need to know the large diameter, subtract the small diameter, and we know we just learned in algebra that you cannot divide that by the length of taper till you solve it. So remember, you have to have one number here. So big D minus little d, divide that by the length of the taper, and then multiply your answer by 12, and that will equal your taper per foot. Okay, so just as an example, let's pull up the calculator, and we'll just put it over here for a sec. So let's imagine that your big diameter equals, let's say, 3 inches in diameter, and let's say your small diameter equals 2.4 inches in diameter, and let's say the length of taper is 6 inches. Okay, so we'll just call up our calculator. So 3 inches is your large diameter, so 3 minus 2.4 equals 0.6. You're going to divide that by 6 inches. You get 0.1, and then you multiply that by 12. Now you may be wondering, why do I multiply that by 12? Well, 12 inches in a foot, right? Because you're solving taper per foot. So if we were solving taper per inch, we just wouldn't multiply this by 12, right? That would tell us how much that part changes in size every inch, not over 12 inches. So what we just learned is that the taper per foot, or how much this part changes in diameter over 12 inches, is 1.2 inches. So this small diameter here, notice this is not 1.2 inches smaller than this. That's because it's only 6 inches long, right? If this were 12 inches long, then this diameter would be 1.2 inches smaller than this. It would be at 1.8 inches. Okay. Clear? Questions? Okay. Good. You guys are going to make this really, really easy. All right. Let's...
It's not clear, but I wouldn't know what questions to ask.
Who's that, Matt?
Yeah.
Okay.
It's so unclear that I wouldn't even know what the clarifying question would be.
Okay. Well, we'll keep going, and then we'll come back to it. Okay, we'll come back to it, Matt. Let's do this. Let's clear our canvas, and let's Control V. It's gone. Just grab it here. All right. Let's go to tailstock offset for a moment. So in our lesson plan, I mentioned to you guys that I gave you the formulas. So if I want to set up my tailstock to create a taper, the formula looks like this. So let's just first put tailstock offset. So this is about you standing in front of the machine, and you need to push the tailstock away from you. Okay, we're not talking about towards the headstock or away from the headstock. We're talking about across the ways, okay? So there, if you didn't know, the upper casting of the tailstock will move independently of the lower casting, and the lower casting is attached to the ways, okay? So you can loosen either bolts or set screws, and you can then push the tailstock away. It can't move too far, but you really don't need it to move that far because it magnifies that adjustment over the length of that part. Or you can pull the tailstock towards you, depending on whether you want the taper to taper towards the headstock or taper towards the tailstock, okay? So tailstock offset, the formula looks like this. TSO, tailstock offset, equals the taper per foot times the LOW this time. Will that be on a test? Yup. Divided by 24. Taper per foot times the length of the work. Okay, so what I'm going to do is I'm just going to slide my screen over for a second and imagine that your part is, oops, sorry. You get what you get here, guys. All right, so you imagine that your part, let's say, is 23 inches long. So the taper's not 23 inches long, the part is. And why that matters is because, as I mentioned before, that your headstock, right, your headstock, you will have the dead center in the headstock, okay, against the faceplate, okay, and it will have a drive dog on it that will spin your part. And then you will have back here in your tailstock, you will have the other center. So your part is sitting between centers. So as I take my tailstock here, this is my tailstock hand wheel, okay? As I push the tailstock away from me, okay, it will only move so much. It might only move an inch, okay, at maximum travel. As I push the tailstock away or I bring the tailstock towards me, you can see how the whole length of this part, right? The whole length of this part, this end will move, right? But the whole part will move so much, right? Not just this end. The whole part will pivot in here. The whole part will pivot right there. So you will, to figure out how much to push the tailstock away or how much to bring it towards you, which is this, right? How much do I move the tailstock? I have to know a few things. I have to know the taper per foot. Well, if this is the same part as before, we figured out that the taper per foot was it 1.4 or whatever it was. Let's just imagine, let's say it's 1.4. So if our taper per foot was 1.4 inch taper per foot, like we solved, this taper per foot right here, right? How much this part tapers between here and here. We'll say TPF equals 1.4. Okay, so the part gets smaller, 1.4 inches over 12. Now the part's only 6 inches long, so that's how we ended up with this. So 1.4 times the length of the work, so times 23 inches. So the taper is only 6 inches long. This is not to scale, right? I don't need to write that, but you guys know. This is only 6 inches long. The whole part is 23 inches long. So I multiply the taper per foot by the length of the work, and then I divide that by 24, and that is going to give me my tailstock offset. So if we bring the calculator up again, oh, it was 1.2. All right, but let's say 1.4. 1.4 times 23 divided by 24. So our tailstock offset, or the amount of actual physical distance we have to push the tailstock away, would equal 1.34. So TSO equals 1.34 inches. Now, this may be an unrealistic movement, because we're just spitballing numbers. Now, some tailstocks will move that. Some will move more. I mean, you can have tailstocks that can move 6 inches, right? All depends on the machine. But if you need to know how much to move that tailstock, this is the formula, and it's deadly accurate. And as far as this class isn't obviously for how to physically do this in the machine shop. Obviously, you have to know, once you loosen those bolts, there's no indicators, there's nothing on the tailstock. So if you start moving it, with an Allen key, you got to know how far to move it. So we do that by means of plunge indicators. And you watch the indicator fall away the distance that you want. Okay, so that's our tailstock offset formula. Okay, the next thing that we want to do here is we want to look at the formula for setting up the compound rest. So imagine again, actually I could probably just take this part. I don't know if I can rotate it or not. Maybe I can. No, I'll have to do it on here. Anyway, doesn't matter. So imagine that we're going to cut this part with a compound rest. So now we're not adjusting the tailstock. Our part is going to be on the center line of the lathe. But we have to actually adjust our tailstock, or sorry, adjust our compound rest, right? So that if this is my tool right here, that's my tool, and it's sitting in my compound rest right here. Boy, these skills are amazing. Okay, and this is my compound rest hand wheel. Okay, so as I dial this handle, right, the compound rest will move this way, right, and it's going to move in line with this taper. So I have to adjust my compound rest this way or this way, so that as I dial the handle on the compound rest, it will travel the direction that I want it to travel. Now, again, this could be a very unrealistic taper, or it could be very realistic depending on how big I draw my compound rest. If I've drawn it bigger, then yeah, this is an easy taper. But you're limited because your compound rest, it only has so much travel, right? It sits on ways. Right, it sits on ways here. So it's when you dial it out and it gets to the end of those ways, you can't go any farther. And you dial it all the way back, it's going to come to the back side of those ways. It can't go any further. So it doesn't have very much stroke. Whether it has 1 inches, 2 inches, 3 inches, depends on the machine. But if you're trying to create a long, shallow taper, you may fall inside that window of your compound rest being able to be used. But if it can't, you're better to know that before, right? So you want to know what's the limit. How far can my compound rest move? So if you want to know that, set your compound rest up. So usually this is 90 degrees, right? If you have it set up like this is your workpiece at the top, and this is your compound rest coming in here. That's 90 degrees. If you set your compound rest up at 0 degrees and you max it all the way back, put a plunge indicator on the front, and then max it all the way forward, and how far your needle goes around on your dial indicator will tell you what the maximum stroke of your compound rest is. So if your taper is longer than that, and remember, now you're talking about a linear distance, right? You're talking about the distance of this line. If the distance of this line, your hypotenuse, is longer than the stroke of your compound rest, then you wouldn't want to set up this way. And it's unfortunate that a lot of times that's how we find out. Is we find out we ran out of stroke about 100 thou before we get to the end of our taper. So just good to think about those things in advance. But how do we use, if we're going to use the compound rest cut a taper, what's the formula look like? So the formula looks like this. So this is for your compound rest. Okay, so this is what the formula looks like. Tangent of half the angle equals taper per foot divide by 24. Notice that the very first formula we learned is taper per foot, how to solve it, right? So now we use it for our other formulas. And you'll see that a lot in machining, especially with threads. You need to solve pitch before you can use pitch, right? And pitch is in a lot of the formulas for threads. So in this instance, we need to know taper per foot, just like we needed to know for tailstock offset, we need to know taper per foot. So good idea, solve your taper per foot at the beginning, because then you can use it in your formulas coming up. But notice here, what we're solving, the compound rest setting is this. You know how your compound rest, it swivels, right? So we're trying to figure out the swivel, right? It's sitting at 90 degrees. How much do I swivel that? Better yet, if it's sitting at 0, right? How much do I swivel it? That's what we're trying to solve. And a lot of people ask, why is it tangent of half the angle? Why are we solving half the angle? Has anybody got any thoughts on why that's what we're solving for? Why are we solving half the angle?
Because we're only going on one side, so it's
Yep.
half the diameter.
Yeah, you got it. So this is our center line, right, of our part in the lathe. So when we set up our compound rest, we're on this side of center line. When I take a cut, I'm only cutting one side. So if I solve half of the angle, whatever I do to this side happens on the other side. So I solve half the angle because I want to know what this angle right here is, right? So I want to know that angle. I want to know this angle because this is the angle that's going to be created if I cut this angle. And I know this is a little hard, you know, especially if you have troubles with trig, okay? But remember, if we, these are two right angle triangles, okay? So essentially what we're doing is we're figuring out what this angle is. We don't have to worry about what's in the middle because these are two horizontal lines. It doesn't matter if they're that far apart, that close together, or if this is just a triangle. It doesn't matter because the angle, remember we learned in geometry that the height of this side is controlled by this angle, and the length of this side is controlled by this angle, right? So these triangles, it's about the opposite side that matters. So if we take that and we cut that cylinder out of the middle and just put those two triangles together, it doesn't change these angles at all, does it? These angles stay the same. There's no change. So I can actually make the distance between, here and here greater, or I can make it smaller, right? So I can get a larger diameter piece of work or a smaller diameter piece of work. It does not matter how much material is in between these two triangles, because this angle does not change. And that angle and this angle are the exact same angle. These are two mirror image triangles. You'll see how this benefits us in just a moment. Okay, so we're solving tangent of half the angle. So essentially what I'm solving is this. All right, I want to know, let's say this is my triangle because this is the side I'm cutting on. Okay, I want to solve this angle right here. That's this. It's actually half the angle because this is the whole angle. So this is only half. So tan of half the angle equals the taper per foot divided by 24. So let's just go back to that 1.4. I know it was 1.2, but tan of half the angle equals 1.4 divided by 24. So we call up our calculator here. 1.4 divide by 24 equals, so 0.0583. So tan of half the angle equals 0.0513. We'll just say 5/8, 3 decimal place, okay? What have we solved? We have converted a common fraction into a decimal fraction. That's all we've done. In trigonometry, remember in our second lesson in trig, we were solving angles. And to solve an angle, you got to do the second function, or shift, right? So we're dealing with tangent. So while this is in your calculator, 0.058, just press on your calculator the second function button, or it may be shift, okay? Then press tan equals. Okay, so let's go to our calculator. Do I have the trig functions here? Okay, second function, tan, gives me, notice, 3.34 degrees. Okay, so that gives me 3.34 degrees. So what this second function, tan, right, we're dealing with tangent, what this does is it converts a decimal fraction into a decimal degree. So this is 3.34 degrees. So what that means is that we take the compound rest, swivel it to 0, and then, you know, around the circumference of the compound rest at the base there's your protractor. So you want to swivel it to 3 and about 1/3, right? Because most of those protractors go in single degrees. They're not super accurate. So you could say closer to 3.5 degrees than 3 degrees, right? If you want to be really, really accurate, you can swivel that compound rest by using a sine bar and gauge block buildup. And I obviously can't show you here, but you can have that shown to you. Rob will probably be happy to do that. But that will get you, you can actually set an angle very, very close to 3.34 degrees using a sine bar and gauge block stack. So now what you've done is you've swiveled that compound rest 3.3 degrees approximately, which means that this included angle, this angle is going to be what? What will this angle end up being if you've swiveled your compound rest 3.34 degrees? Anyone? What will this angle be? We just solved this one. So what will this one be? It will be 6.68 degrees. Twice this, because we're only solving half the angle, right? So this included angle is going to be double. So this is a very common way to create a taper. But a lot of times what you'll see is you'll see the actual included angle, what the manufacturer wants, they'll call out on the print. They'll say this included angle is 5 degrees. So then you got to work backwards, right, to figure out if you have the angle, you got to work backwards to figure out what is your taper per foot, right? So algebra, we just solve for the unknown, move things to the other side of the equal sign. In solving tapers, these are the key formulas that we will use. So just as a reminder, okay, just as a reminder, when you go to solve unknown information in your taper assignment, when you're looking for taper per foot, which you're going to notice on your assignment, I get you to solve that first. You need the large diameter, you need the small diameter, and you need the length of taper. Okay, that's going to give you your taper per foot. Times 12, because it's over a foot, right? Now, sometimes what happens is on a print, and this is pretty typical, you may have the large diameter information, and you may even have the small diameter information, but what you don't have is the length of taper. Or you may have the large diameter and the length of taper, but you will not have the small diameter. So I'm going to just walk through one example of one of these other missing pieces of information. And the one I'm going to show you is the missing small diameter. And why I want to show you that is because that's the hardest one to solve. Okay, so pay close attention to how I solve this. Okay, so this applies to, whoops, let's just go here. This applies to solving the unknown small diameter with this taper per foot formula. So I'm gonna just switch over to blue. Taper per foot equals, let's say the large diameter is, I don't know, let's say it's 4 inches minus the small diameter. Let's say the length of the taper is, let's say it is 10 inches and 12. So notice here we have 2 pieces of missing information, right? Well, you can't solve that if you have 2 pieces of missing information. We do need to have only one, right? And that's the same as any algebra. So let's plug in a taper per foot. Let's say the part tapers, I don't know, let's say 0.5. Let's try and keep this sort of easy. So this part, by the time you get to the small diameter, over 12 inches, it will taper 0.5 inches per foot. Okay, so let's move things around to solve for the small diameter. So we rewrite this. 0.5 equals, so we want to start moving things around. The easiest thing to move is the multiply by 12, right? So times 12 divided by 12, right? They cancel each other out. But whatever I do to this side, equal sign has to remain true. So I have to divide this side by 12 to make this formula true, right? So how this looks right now is 0.5 divided by 12 equals 4 minus d divided by 10. Okay. The next easiest thing to move is the divide by 10. So 0.5 divided by 12 equals 4 minus d divided by 10 times 10. So these two cancel each other out, but that means I have to multiply this side by 10 to make it true, right? So remember when you cancel each other out, I showed you that example a couple of weeks ago, right? If I divide one number by another and then I multiply it by the same number again, what did I do it for in the first place? The answer is just what the number you started with. And that's what's happening here, okay? But the equal sign has got to be true. So if I multiplied this ratio by 10, I have to multiply this ratio by 10. Okay. All right. So what our formula looks like now is 0.5 over 12 times 10 equals 4 minus d. Okay. And what's easy? Well, what do we got to move? We got to move the 4, right? We've got to move the 4 because we want to isolate the d. So let's do that. 0.5. Oops, sorry. Okay, 0.5 divided by 12 times 10. This is a positive 4, right? Okay, so sign numbers, any number that doesn't have a sign in front of it is a positive number. And all numbers have a sign, right? So you don't see a sign, that means there's a plus there. And that plus belongs with the 4. this negative sign belongs with the D. Okay, always. Every single number is a positive number or a negative number. So when you take 10 and subtract 5, that's positive 10, negative 5. And you end up with positive 5, right? So every sign belongs to a number. So in this case, every number has a sign attached to it is the proper way to say that. So if I move this 4 to the other side of the equal sign, then what I need to do here is I have to recognize that a positive 4 can only move over if you subtract 4, right? 4 minus something minus 4, it would cancel out the 4's, right? So let's leave a space there and say equals 4 minus D minus 4. And therefore this positive 4 and negative 4, they cancel each other out. But whatever I did to this side, I got to do this side. So I have to subtract 4 from this side. So now our formula looks like this. 0.5 divided by 12 times 10 minus 4 equals what? What does it equal? What am I left with?
Negative D.
Thank you. Negative. That negative sign belongs with that D. Okay, so very first thing that you should notice about this is what you're trying to solve is a negative number. Our small diameter can't be a negative number. But let's go through the motions. Let's solve this so that we can get the answer. All right, let's get our calculator out here and let's do the formula. 0.5 divided by 12 times 10 minus 4 equals. Notice that our answer is negative 3.95. Negative 3.95 equals negative D. So just think about the math here for a second. What we're stating is that negative 3.95. So 3.95 units to the left of a 0 on a number line equals negative D. So basically what we're saying is the small diameter here, right? The small diameter here, we didn't solve. We solved the small diameter on the other side of the equal sign, the negative small diameter. But remember what we just learned in algebra here? We know this has to be positive. We know this has to be a positive number. We can't create a negative size. We can only create a positive size, right? So this has to be a positive number. Notice what we did all through this equation. Every time we wanted to move something to the other side of the equal sign, we had to do the opposite. Here we had a positive 4 minus 4. We had to subtract 4, and on this side it's minus 4, right? So if I want to, basically what I'm doing is I'm taking this 4, how this algebra works is I'm taking this 4, this positive 4, and I'm just putting it over here. As soon as it crosses that equal sign, it becomes its opposite, a negative. So really, I'm not saying plus 4, negative 4. What I'm saying is I'm going to take this 4, I'm just going to put it here. As soon as I do that, the sign changes from a positive to a negative. Same up here, right? I took this 12 right here, and I want to move it over here. As soon as I take this, multiply by 12 and put it over here, it becomes a divide by 12. That's all we're doing. I take this divide by 10 and I want to move it over here. It becomes a times 10 because it does its opposite. It does the opposite, right? So we get all the way down here. I have a minus 3.95 equals minus D. I'm going to move my minus D over here, and I'm going to move my minus 3.95 over here. I'm going to move each of them to the other side of the equal sign. And what that gives me is D equals 3.95. That's all we're doing. We're just moving them to the other side of the equal sign, and the sign changes with it. So the truth is,